We're looking at finding real zeros of a polynomial. We have all these rules in front of us that we learned last class period to help us to break down and find those zeros of a polynomial. We have our factor theorem that says if x minus c is a factor, then f of x, if and only if f of c would give us back 0. So it goes both ways because it's an if and only if statement. So if f of c equals 0, then x minus c has to be a factor of f of x. And if x minus c is a factor of f of x, then f of c must equal 0. We know that the degree of our polynomial are that we can't have more real zeros than that degree. And then we have this rational zero theorem. And so this rational zero theorem, basically what we're going to do is we're going to look at a sub 0. P is factors of a sub 0. And we're going to look at a sub n, the leading term, coefficient of the term. And those are factors. Q is factors of a sub n. And then this theorem says that if we have a rational zero of our polynomial, it has to be in the form of P divided by Q. So it has to be in that list that we'll write out of the factors of a sub 0 divided by the factors of a sub n. So this theorem does not give us any of the irrational zeros, and it doesn't give us any of the complex number zeros. That would give us zeros of a polynomial, but it does definitely help us break it down a lot. And so let's look at the following example, and let's just look at the possible zeros of this polynomial. It tells us not to solve for it. So looking at P is equal to factors of 20. And so let's go in here and let's write out a list from smallest to largest. I'm going to put plus or minus because negatives can divide in here evenly too, that go into 20. So 1 goes into 20 evenly, 2 goes in there evenly, 4 goes in there evenly, 5 goes in there evenly, 10 and 20. And now let's look at factors of our leading coefficient. So factors of 6 are going to be 1, 2, 3, and 6. So if we look at P divided by Q, we're going to look at all the different possibilities of these rational numbers. So starting with 1, I'm going to look at 1 and I'm going to divide it by each Q value. So I have 1 divided by 1 is 1. I have 1 divided by 2 is 1/2. I have 1 divided by 3 is 1/3. 1 divided by 6 is 1/6. So now I'm going to go to the next number in my list of P, and I'm going to divide it by each Q value. If I get a number, when I simplify it, that is already in our list of P over Q, I'm not going to list it twice. So I have 2 divided by 1, which is 2. 2 divided by 2 is 1, but we already have that, so I'm not going to rewrite it. 2 divided by 3 is 2/3. 2 divided by 6 is 1/3, but that's already in our list. So go to our next number, 4, and do the same process. So 4 divided by 1 is 4. 4 divided by 2 is 2, already listed. 4 divided by 3. And 4 divided by 6, which is 2/3, reduced, and we already have that one listed. So now going to 5. 5 divided by 1 is 5. 5 divided by 2 is 5/2. 5 divided by 3. And 5 divided by 6. Go down the list with 10. So 10 divided by 1 is 10. 10 divided by 2 is 5, already listed. 10 divided by 3. And 10 divided by 6, which reduces to 5/3, which is listed. So 20 divided by 1 is 20. 20 divided by 2 is 10, I already have it. 20 divided by 3. And 20 divided by 6. 2 goes into both of those. So that would be 10^3, which we already have. So we've narrowed down our list of real rational zeros. Remember, integers were rational numbers because we could rewrite that as over 1. And so we've narrowed down out of the infinite number of possibilities, we've narrowed it down a lot. So let's now look at an example where we kind of put it together and find the zeros of the polynomial. So the directions for the next problem says use the rational zero theorem to find all the real zeros of each polynomial function. Then we're going to use the zeros to factor f over the real numbers. Okay, so we're going to look at our p-values, which are factors of our constant. And so values that go into 8 evenly are plus and minus 1, 2, 4, and 8. Then if I look at my Q value, and this is always the nicest case when your Q value is actually 1. So factors of 1 are just positive and negative 1. So now when we look at P divided by Q, you have plus or minus. Excuse me. 1 divided by 1, which is 1. My morning sneezes. Sorry. So 1 divided by 1 is 1. 2 divided by 1 is 2. 4 divided by 1 is 4. And 8 divided by 1 is 8. So our only possible rational zeros of this polynomial f of x are plus or minus 1, 2, 4, and 8. So we were using synthetic division to see if we could find the zeros. We're trying to use synthetic division and see if we can get a 0 as our remainder. So recall, for synthetic division, we're going to write down the coefficients from descending order of powers, and if there's any missing degree of our term, then we would put a 0 there. So x to the 4th, our leading coefficient is 1. X cubed, we have a -1, x squared, so -6, x is 4, and our constant is 8. Then we brought down our first term, which is 1, and we multiplied it by our c value, which I'm using as 1 right now. So 1 times 1 is 1, and we sum the column. So -1 plus 1 is 0, and we repeat the process. So 1 times 0 is 0. Sum the column, -6 plus 0 is -6. 1 times -6 is -6. 4 minus 6 is -2. 1 times -2 is -2. And 8 minus 2 is 6. So because this is not a 0, this is not a 0 of my polynomial. So now let's move down the list. So let's just try 2. So we have 1, -1, -6, 4, and 8. So bring down our number 1. 2 times 1 is 2. -1 plus 2 is 1. 2 times 1 is 2. -6 plus 2 is -4. 2 times -4 is -8. 4 minus 8 is -4. 2 times -4 is -8. And we get a 0 here. And so that makes us really, really happy. We found one of them, and that's going to help us break this down. So x equals 2. I'm just going to put it up here for now. These are our zeros. And our factors, and let me just put linear factors. Well, if x equals 2 is a 0, then x minus 2 is a factor. So right now we have broken down f of x. F of x is equal to our factor that we just found, the x minus 2, times this quotient. So this quotient here, remember these numbers down in that bottom row of our synthetic division were actually the coefficients of our quotient. And we started 1 degree less than what polynomial degree we were using up here. So this is degree 4, so I know I'm starting with a cubic. So this is the coefficient in front of x cubed, so I have 1x cubed plus 1x squared minus 4x minus 4. So if I continued with this, I would, and I actually see I can factor this, and so I would actually factor it now. But I want you guys to see that this is not always the case, and how to break it down further. So instead of using synthetic division on my original function, I would use synthetic division on my cubic. Notice that we can look at P over Q here. And if I look at P over Q of my cubic function, P is not 8 anymore, it's 4. So notice that 8 can no longer be a possibility in here. I've already tried 1. And if 1 is not going to be a factor of f of x, it's not going to be a factor of our what we got to be our quotient. And so I would list down my numbers from this cubic. And so we have 1, 1, -4, -4. It's possible, we found 2 is a 0, but it's possible 2 is a 0 again. So we could test it again and see if we get back 0 as our remainder. So if we bring down a 1, we have 2 times 1 is 2, 1 plus 2 is 3, 2 times 3 is 6, -4 plus 6 is 2, and 2 times 2 is 4. So notice that x equals 2 is a 0 again. I'm just going to put 2 here again, but normally we wouldn't say that x equals 2 and 2 is a 0. We would say right now x equals 2 with multiplicity 2 is a 0. Notice that when we had done this top row, this was a cubic. So this down here, this bottom row has to be a quadratic. So this is 1x squared plus 3x plus 2. Once you get down to a quadratic, factor it, or we might have to go in and use the quadratic formula. So far, we've broken down f of x even further. We broke it down as x minus 2 times x minus 2 times x squared plus 3x plus 2. So I notice that quadratic is factorable. There's 2 numbers that multiply to give me positive 2 and adds to give me a positive 3. So x plus 2 times x plus 1. So we just broke this down where all of our factors are linear. And x plus 2 equals 0 when x is -2. So I have -2 is also a 0. And x plus 1 is 0 when x is -1. So our zeros of our polynomial, we have -2, -1, and 2 multiplicity 2. So those are the places that we're going to be either crossing or touching the x-axis. Remember, multiplicity odd. So -2, -1 our odd multiplicity. So we're going to just we'll cross the x-axis there, but at x equals 2, it's multiplicity 2, it's even multiplicity. So we know it's just touching the x-axis on that graph and turning back in the direction it had been coming in. So our next example, we have f of x equals 2x to the fourth minus x cubed minus 5x squared plus 2x plus 2. Looking at this, I want to find the zeros of the polynomial, and I want to rewrite f of x in terms of linear factors. So I'm looking at my p-value. My p-value are factors of my constant. And so my factors of my constant here are just plus or minus 1 and 2. Q, those are factors of my leading coefficient. So factors of 2 are 1 and 2, positive and negative. So now if I look at P divided by Q and get all those different possibilities, plus or minus, 1 divided by 1, which is 1, 1 divided by 2 is 1/2. So now if I look at 2 divided by 1, I get 2, and 2 divided by 2 is 1, but that is already in my list. So I've narrowed it down to 6 numbers that if we have a rational zero, it's going to be one of those 6 numbers, or a multiple. It could be more than one of them. Okay, so let's just start testing. So let's put 1 up here and then write down our coefficients of f of x. We got 2, -1, -5, +2, +2. Bring down our first number 2 and then multiply by c. So 1 times 2 is 2. -1 plus 2 is 1. 1 times 1 is 1. -5 plus 1 is -4. -4 times 1 is -4. 2 minus 4 is -2. 1 times -2 is -2, and we get back 0. So that makes us happy. And so x equals 1 is a 0. And we know that right now we have x minus 1 is our factor. And if we wrote out this list, this is going to be 2x cubed plus x squared minus 4x minus 2. So I could continue on with my synthetic division, but again, if we can factor it, that's going to be a lot faster than going through this process. And so if you have 4 terms, sometimes factoring by grouping works. And so if we group our first 2 terms together, notice we have an x squared in common that we can pull out. So if we pull out an x squared from 2x cubed plus x squared, we're left with 2x plus 1. And then -4x minus 2, let's pull out a -2 from both of those terms. And so we're left with 2x plus 1. So right now, we can factor that. That's the same thing as pulling out our 2x minus 1 or 2x plus 1 from both of those terms. And if we do that, you're left with x squared minus 2. So we're breaking it, our f of x value down into linear factors. So x squared minus 2, that's not linear, it's quadratic. Think of it, it's kind of like a difference of squares. Even though that 2 isn't a perfect square, we can square something to get back 2. We can square the square root of 2 to get back 2. So we can think of this as x minus root 2 times x plus root 2. And let me bring down the other factors, 2x plus 1 and our factor of x minus 1. So we've broken this down into completely linear factors, product of linear factors. And we can list our zeros, which are also the intercepts, x-intercepts of f of x. So x minus 1 is 0 when x equals 1. 2x plus 1 equals 0. Well, you would subtract 1, divide by 2. So we get negative 1/2. And then positive root 2 and negative root 2. So notice our rational zero theorem. All of our rational zeros, which are 1 and negative 1/2, were listed in that list of P divided by Q by the rational zero theorem. Okay, so we have another theorem in front of us that will help us narrow down our search while we're looking for these zeros. And this is called Descartes' rule of signs. So it tells us, suppose f is a polynomial function written in standard form, so descending order of powers. The number of positive real zeros of f either equals the number of variations in the signs of the non-zero coefficients of f of x, or else equals to that number less an even integer. Okay, let's break down what that's saying. So, and let's maybe pull that last example we had and go through and look at this. So this is saying I need to count the change in the signs from term to term. So the number of positive real zeros is either equal to the number of variations in signs of the non-zero coefficients of f of x. So looking at our first term, which is 2x to the fourth, that's a positive term. Or it's a positive in front. And so the next we have minus. So notice this is one change in a sign. So that's a change. But if I go to the next term, minus 5x squared, that's a minus. So from a minus to a minus, that is not a change in signs. So maybe I could put a 0 there. But going from negative 5x squared to plus 2x, that's a change in sign. And then going from 2x to 2, that is positive, and positive, that's not a change in sign. And so looking at the number of changes of signs, there's 2 of them. And so this theorem is telling me that there is either the number of sign changes. So there is either, and this is for positive real zeros. So there is either 2, or we're going to take that number and we're going to decrease it by an even number. I just keep decreasing it by 2 until I get to 0 or a negative number, and it's impossible to have a negative number of zeros. So if I take 2 and I subtract 2, I get 0. So to me, this is telling me there is either 2 or 0 positive real zeros. So if we were going through our process to find our zeros, and we knew that, and we found one positive real zero, then we know that there's another one out there. If you go back up to what we just found as our 0, notice that we had 1 was a real positive 0, and root 2 was a real positive 0. And so we had 2 of them, which the theorem said I was going to have that or 0. So the next part of the theorem helps us find the possible number of negative real zeros. And so if I look at the next piece, we're going to look at the number of negative real zeros of f either equals to the number of variations in the signs of the non-zero coefficients of f of negative x, or else equal to that number less than an integer. So first thing that we have to do is we need to look at what is f of negative x. So if we go in here and we replace this x with a negative x, we want to count and see how many sign changes we have. So I'm just going to go in and I'm going to put parentheses wherever I see an x and go back in there and replace it with a negative x. So we have 2 all times negative x raised to the 4th power minus then quantity negative x cubed minus 5, the quantity negative x squared, 2 times negative x plus 2. Well, if I took negative x and multiplied it by itself 4 times, it would be positive x to the 4th. So this is now, I can rewrite this as 2x to the 4th, negative x cubed, that quantity cubed is negative x cubed, times this negative out front is positive, just positive x cubed. Negative x quantity squared is positive x squared times the negative 5 in front. So this is minus 5x squared. And then 2 times negative x, so minus 2x plus 2. So you're going through and you're counting the number of sign changes. So from 2x to the 4th to an x cubed, that's not a sign change. From x cubed to negative 5x squared, that's one sign change. From negative 5x squared to negative 2x, that's not a sign change. And negative 2x to 2, that is a sign change. And so our theorem tells us there is either the number of sign changes, so there's 2 of them, there's either 2 or 0 negative real zeros. So again, if we were looking for our zeros and we found one of them was a negative 0, we know there has to be another real 0 out there, and to continue to look for it. Okay, this is that piece where you count the number of sign changes and you subtract by an even number tends to get students. And so let's just look at an example, or let's just say we were looking at this and we found that g of x had, let's say, 7 sign changes. Then the possible positive real zeros is equal to the number of sign changes, 7, or that decreased by an even number. So 7 minus 2 is 5. So it could have 5 positive ones. If I take 5 and I decrease it by 2, it could have 3. If I take 3, decrease it by 2, that would be 1. 1 decreased by 2 is negative 1. Again, it's not possible to have a negative number of zeros. So from this, just looking at the sign changes of g of x, there's 4 different possibilities. I'm either going to have 7 positive real zeros, 5, 3, or 1 positive real zero. And we won't know until you found all the real zeros. Okay, so let's use that fact now to help us find zeros of a polynomial. So we have f of x equals 2x to the fourth minus 19x cubed plus 57x squared minus 64x plus 20. And we want to use Descartes' rule of signs to find possible number of positive real zeros and negative real zeros. So we're going to go through and first look at the number of sign changes of f of x. And so if we look at our first term to our second term, we have a 2x to the fourth minus a 19x cubed. So that's a sign change. We have a negative 19x cubed to a positive 57x squared. That's a sign change. We have a 57x squared to a negative 64x. So that's a sign change. And then we have negative 64x to positive 20. So that's also a sign change. So the number of sign changes of f of x is 4. So that tells me there are 4, or subtract that by an even number, 2. And 2 minus 2 is 0. So there's either 4 or 2 or no zeros, positive zeros. And so same thing, number of sign changes for f of negative x. So if we went in here and we plugged in negative x, wherever we see an x, and let's simplify it while we do that. So negative x raised to the fourth power, that's going to be positive. So this is 2x to the fourth. Negative x quantity cubed, there's a negative with a negative in front. So that's going to be plus 19x cubed. Negative x quantity squared, that's positive. So that's 57x squared. Negative x times negative 64, so that's plus 64x. And negative, no, there's no negative x, so just plus 20. So notice there's no sign changes. So that tells me there's no negative real zeros. So right there, that cuts our list in half once we start listing our possible rational zeros. We don't have to look at the negative of those. Okay, so let's look at P divided by Q. I was just seeing if I can drag this down here. Okay, so our p-values are plus or minus factors of 20. I'm just going to put the plus or minus just because, but I'm not going to look at my negatives when I start testing. So numbers that go into 20 evenly would be 1, 2, 4, 5, 10, and 20. Q are factors of our leading term coefficient 2, which is 1 and 2. So if I look at P divided by Q, I'm looking at all of our combinations. We have 1 divided by 1 is 1, 1 divided by 2 is 1/2. 2 divided by 1 is 2, 2 divided by 2 is 1, but it's already listed. 4 divided by 1 is 4, 4 divided by 2 is 2, but it's already listed. 5 divided by 1 is 5. 5 divided by 2. 10 divided by 1 is 10. 10 divided by 2 is 5, already listed. 20 divided by 1 is 20. And 20 divided by 2 is 10, and that number is already listed. So we have 1 up here, and we're going to list our coefficients. So 2, negative 19, 57, 64, and 20. Bring down 2. 1 times 2 is 2. Negative 19 plus 2 is negative 17. 1 times negative 17 is negative 17. Negative 17 plus 57, that is 40. 1 times 40 is 40. 64 plus 40 is 104. I can see that this is not going to work. I get 124, that's not a 0. X equals 1 is not a factor, or is not a 0. So now let's try 2. So 2, negative 19, 57, 64, and 20. So let's, oops. Get that out of the way. Okay, so bring down 2. 2 times 2 is 4. Negative 19 plus 4 is negative 15. 2 times negative 15 is negative 30. 57 minus 30 is 27. 2 times 27, that is 54. I can see this doesn't work. 54 plus 64, that's 118. That doesn't equal 0. So let's do 4. See how I'm skipping those fractions. So I have 2, negative 19, 57, 64, and 20. I made a mistake. I was looking at this and I was like, did I bring down all my negatives? And I didn't. Notice that this was minus 64. So this should have a negative in front of my 64. I don't think that's going to change anything, but let's look at it. So negative 64 plus 40 is negative 24. 1 times negative 24 is negative 24. I still don't get 0. Let's go over here. And so I'm pretty sure I did everything right from there. So 27 goes here. So that would give me negative 37, and negative 37 times 2 is negative 74, and that's not going to give me 0. Put a negative there. So 2, negative 19, 57, negative 64, and 20. So bring down our 2. 4 times 2 is 8. This gives me negative 11. 4 times negative 11 is negative 44. 57 minus 44, that's 13. 4 times 13 is 52. If I sum this up, I get negative 64 plus 52. What is that? Negative 12. That's not going to give me a 0 there. Let's try 5. So bring down 2. 2 times 5 is 10. Negative 19 plus 10 is 1. 5 times 1 is 5. 57 plus 5 is 62. 5 times 62 is 310. I can see right away, this is not going to give me 0. I can also see that these are all positive numbers. I didn't give you that theorem, but that says that if you get all positive numbers when your C value is positive, then that is an upper bound. There's no other 0 higher than that number that could work. And so I know that I can exclude looking at 10 and 20 because of that theorem. That means I got to go back and I got to check my fractions. And so let's look at 1/2. So putting our numbers up here, we have 2, negative 19, 57, negative 64, and 20. Bring down 2. 1/2 times 2 is 1. Negative 19 plus 1 is negative 18. 1/2 times negative 18 is negative 9. 57 minus 9 is 48. 1/2 times 48 is 24. Negative 64 plus 24 is negative 40. 1/2 times negative 40 is negative 20. That's a 0, and it makes us happy. So x equals 1/2 is a 0. X minus 1/2 is a factor. If we write down this quotient, these are our coefficients of our quotient, 1 degree less. Our degree we started with was degree 4, so this is going to be cubed. So this would be 2x cubed minus 18x cubed plus 48. Oops, that's minus 18x squared plus 48x minus 40. Let's see if we can factor by grouping. So if we do this on the side. So if we group the first 2 terms together, we could pull out a 2x squared. Pulling out a 2x squared from those first 2 terms, we're left with an x minus 9. Yeah, that's not going to work, is it? I can pull out a 4. There's nothing I can pull out of 48 minus 40 to give me x minus 9. So that's not going to work. Okay, so I'm going to start repeating the process, but this time I'm going to repeat it with this polynomial. I don't want to look at the P over Q at all. Let me just see. Let's look at the sign changes though. So if I look at the sign changes from this polynomial, I have 1 sign change, 2 sign changes, and 3 sign changes. So that tells me that there's either 3 or 1 real positive 0. We already found 1. If we find another one, then there has to be actually 2 more. Let's keep with our list. We already tried 1, we tried 2, we tried 4, we tried 5. We saw that we didn't need to do 10 and 20, and I explained why. But let's see, maybe 1/2 works again. Could have a double multiplicity. So let's go back and then let's do it though for these numbers. So this is going to be 2, negative 18, 48, and negative 40. So if I bring down 2, 1/2 times 2 is 1. Negative 18 plus 1 is negative 17. Negative 17 times 1 is negative 17 halves. I'm going to need a common denominator. So multiply 2, that's 96 halves minus 17 halves. Which gives us 79 halves. Times 1/2, that's 79 fourths. Not 0. So we could try 5 halves. Again, let's use that bottom row. So of this polynomial, just because it's broken down further, 2, negative 18, 48, and negative 40. So bring down 2. 2 times 5 halves. That's going to clear my 2's and leave me with a 5. Negative 18 plus 5 is negative 13. That's going to give me negative 13 times 5. That's negative 65 halves. So I have 96 halves minus 65 halves is 31 halves, and that's not going to work. So it looks like there's only one real rational 0. I'm going to pause the video and I'm going to pull up Desmos and I'll pull it in. Something wrong somewhere. If you look at this picture of the graph, our x-intercepts, notice that this x equals 2 is a 0. X equals 0.5, which we found, and x equals 5. So I must have done something wrong with my math when I was doing the synthetic division. Actually, it's not. I still have the intermediate value theorem. Okay, let's take a break though. I wanted to finish that problem before we took a break. Didn't realize it was going to take that long.